Let's work on a central limit theorem problem. So we have the same unfair four-sided die that I've been working on in the past couple problems. The expected number of twos in three rolls. So I'm rolling this four-sided die, so it's unfair. I'm rolling it 3 times and I'm counting the number of twos, and the expected value for the number of twos is 1.2. So let's write that down. My expected value, or the average number of twos in 3 rolls, is 1.2. So if I rolled it 3 times, counted the number of twos, and I did this over and over again, I would start to see that the average converges to 1.2. We also know that the standard deviation is given to us by 0.849. Okay, so we roll this dice 3 times and record the number of twos. We then repeat this 50 times. We obtain an average of 1.5 twos in 3 rolls. So we roll it 3 times and we're getting roughly about 1.5 twos in those 3 rolls. Using the rule of thumb that 2 standard deviations away from the center is significant, is this significant, right? So our expected value is 1.2, we're getting 1.5, so a little bit higher than what we were expecting. Let's see if it's 2 standard deviations away. And after we answer that, we want to answer, what is the probability of obtaining an average this large? So because this is a central limit theorem problem, let's remind ourselves of what the central limit theorem tells us. So the central limit theorem tells us that if x is any distributed variable with an average mu and a standard deviation sigma, then the averages of x will be normally distributed with the same average, right? That mu and that mu, it's the same symbol, it's the same number. And the standard deviation of my averages is given to me by the standard deviation of the original distribution, but now divided by the square root of n, where n is the number of data points that gave me that average. So in our case, because we're counting the number of twos in 3 rolls, the original distribution was a binomial distribution. The average was 1.2, and the standard deviation was 0.849. This is going to imply that the average number of twos in 3 rolls is normally distributed with the same average, right? That mu and that mu is 1.2. And my new standard deviation is given to me by 0.849, right? My original standard deviation divided by the square root of n. So how many times did I roll this dice? 3 times. So I had 3 rolls 50 times. So I took 50 different averages. All right. So the average number of twos, let's go ahead and tell ourselves what these numbers are. The standard deviation for the number of twos is about 0.12. Okay, so if I know that my averages are distributed normally, let's go ahead and draw that curve. I have a normal distribution, and it's centered at my expected value of 1.2. And let's put up here that the standard deviation of the averages is 0.12. So let's title this. This is the distribution of the average number of twos in 3 rolls of this dice. Okay, so the first question, using the rule of thumb that 2 standard deviations away from the center is significant, is this significant, the fact that we have an average number of twos of 1.5? So 1.5 compared to 1.2, that's somewhere over here. Right, the question is it 2 standard deviations away? So if I take 1.2 and I add 2 of my standard deviations, well, that's 1.2 plus, this is the distribution of the average number of twos. So the standard deviation that I should use is the standard deviation of my averages given to me by the central limit theorem. And if I do that, I end up with 1.44 roughly. All right, so 1.44 is 2 standard deviations away from 1.22. So where's 1.4? Let me underline this. 1.44 is somewhere right there. So 1.5 is significant. It's more than 2 standard deviations away. In fact, we could have gotten here in another route. If I just calculate the z-score of 1.5, it'd be 1.5 minus the average of 1.2 divided by the standard deviation, 0.12. So the z-score of rolling an average of 1.5 twos out of 3 rolls is 2.499, right, or about 2.5. So the z-score is greater than 2, right? This average of 1.5 is more than 2 standard deviations to the right of our expected value. So that's more than 2 standard deviations. All right, now the second part of the question. What is the probability of obtaining an average this large? So this is the distribution of the average number of twos in 3 rolls. It's centered at 1.2 and has a standard deviation of 0.12. If I want to find the probability of obtaining an average greater than my measured value of 1.5, I'm looking for the area in the right side of that distribution, right? The area in that tail. All right, so how can I get the area in the tail? Well, I need to turn this into z-scores. Our critical value sheet uses areas to the left of z-scores. So the z-score of my average, the z-score of 1.2 is going to be 0. And the z-score of 1.52s out of 3 rolls, we've actually already calculated that over here. So the z-score of 1.5 from this distribution is 2.5, roughly. So I can find this area by finding this area. And I can get to this area by taking 1 minus the probability of having a z-score up to positive 2.5. And I do that because this is on my table, right? My table has areas to the left of positive z-scores, right? So if I take 1, if I take area underneath everything and subtract off the area up to 2.5, I should just be left with the area in that tail. And if we do this, we read our table and find that the area to the left side of 2.5 is 0.9938. So the area that's inside this tail is then 0.0062. Or if I move that decimal over twice, 0.62%. So we only had a 0.62% chance of rolling 1.5 twos out of 3 rolls, or rather rolling an average of 1.5 twos out of 3 rolls, given that we were supposed to roll an average of 1.2.